Hello, so in this video, we're going to kind of carry on talking about this simple random walk. This is pretty much, this is just going to be the last video talking about this simple random walk model video. So just to recap again, is you just start, the whole idea behind a simple random walk is you start in the center, start at some point, and we call that, 0. Then either you can move right or left by one step, effectively. And as you move through each time period, so you increase your time, so time equals 1, time equals 2, time equals 3, you basically increase. You can either move right or left from your previous position, okay? And in the last video we tried to define this probability. So what is the probability, given that we're at a certain position and we've taken a certain number of steps? What is the probability of us being in a certain position? So say, for example, at position 3 or position 1, okay? Given that we're at a certain position, what is the probability that we what is the probability that we're at a certain position, given that we've taken a certain number of steps, okay? And that's kind of the whole idea with what we were doing last time. And if you remember, we just kind of finished off with this thing. It was defined as, it's a bit like, probability is really number of ways of something happening over the total number of objects, if you like. Okay, so if you like, if you have a bag of green counters, if you have a bag of 3 green counters and a bag of 2 red counters, okay, the probability of pulling out a red counter is 2 out of 5, because you've got 5 counters in the bag in total, and 2 of them are red. Likewise, the probability of being green is 3 out of 5, because you've got 3 counters of green and 5 counters in total, okay? So it's a bit like that. Well, it's exactly the same as that, in fact. Okay, and we basically said, well, the number, so it's the number of n step paths that end at a particular position. So n step is just the number of steps that you've taken. Okay, so it's the number of, say, 3 steps or 4 steps or 6 steps or 2035 steps, whatever. It's the number of n step paths that end at a particular position, n. So, for example, position 3, okay, or position of -3, doesn't matter. Right, out of all of the total number of n step paths. So the total number of n step paths is basically, say for example, if you take a 3-step path, then how many different paths can you take? Well, we said that it's going to be, this thing on the bottom is just going to be 2 to the power of n. So if there's 3 steps, because there's, the reason why it's a 2 to the something, the 2 just dictates because you can either move 2 directions, you can either move left or right, okay? Okay, so if you take 3 steps, the number of different paths that you can take at the end of those, those 3 steps, you'll have 8 different paths to choose from, effectively. Okay, so that's what that thing contributes to. And this thing on the top corresponds to a factorial. It's effectively n factorial over a factorial. Remember, a factorial is just the number of steps taken to the right, multiplied by n minus a factorial. So n was just the number of steps that you've taken, okay? And so therefore what we'll end up with is n factorial over a factorial times n minus a factorial, okay? All divided by 2 to the power of n, okay? And of course we can do a little bit of simplification and we could just write it like this, so 1 over 2 to the power of n times that thing, because of course it's just being divided. Okay, so that's where we ended up in the last video. Now in this video, okay, so at the moment we've just been considering discrete, what's known as discrete time steps. So in other words, you have definite time steps. You can only end up at a certain value. Okay, so you start here, say, you can only move to 1, 2, 3, etc., or -1, -2, -3. Those are the only positions that you can end up. Okay, but what we now want to do is basically say, well, actually, why do we have to just end up at a certain definite step? Why can't we, so basically, at the moment we can't end up between steps, if you like. But now what we want to do is we want to consider what's known. So this is the discrete case. Okay, but the continuous case is basically where you can end up anywhere along this number line. Anywhere along this, let me draw that out again. Anywhere along this number line. So we can start at 0, okay, and we can end up absolutely anywhere we like. So we can end up over here, we can end up in there, or over there. We can end up absolutely anywhere we like along this number line, okay? And that's what's known as the continuous case. Continuous. So the way that we're going to do this, is by simply, if we just consider one step. So this is one step, say from 0 to 1, okay? And this is a discrete case, so we can either end up at 0 or we can end up at 1. So I'm just considering now one step that we can take. And let's say, for example, let's just for argument's sake, consider from the range, from the step from 0 to 1. So from the step from 0 to 1, okay? And basically, the way which we're going to do it is rather than taking them one big step, so the discrete case is where we take one big step. The discrete case is just where we take, if you like, one big step, so from 0 to 1 or from 1 to 0 or whatever. Okay, so just one step. Whereas with the continuous case, what we're going to do with the continuous case is we're just going to take lots of small little steps, lots of tiny, tiny little steps. Okay, and the idea being, so lots of small steps. That as we take more and more steps, what we're effectively doing is we're just considering anywhere along a straight line. We're effectively smoothing out a straight line, so we can kind of move anywhere we like along this line. It's almost smooth. If you like, it's almost it's a snail which is gliding along the ground. Yeah, it's just sliding on the ground in one smooth little motion. Whereas this is, if you like, a definite step. Whereas this is almost just like a smooth motion, like a snail. Okay, and this is the continuous case. So we're going to do it basically. We're going to do it by taking more and more time steps, okay? And that's basically the idea of what we're going to do. So now this is where we introduce our notation, which I said before wasn't really that useful, but now it comes into a lot of useful. So, for example, we had m, which counts as position before, okay, and then we move by some distance, okay. Well, now obviously before we were moving by the same distance each time. We're moving by 1. Each time. So delta didn't really matter. That's just the distance that we move. Okay, delta is just the distance we move. So delta is the distance that we move in each step. Okay, so before delta didn't really matter. Okay, we just defined m as just our position. Well, now what we're going to do is we're going to now have to use m because we're now going to have to use delta because we're no longer moving by one big step. We're now moving by lots of tiny little steps. So we want to kind of consider delta. Okay, and we're just going to define this as x. So now our new position is just going to be is now just going to be our m times our delta. And likewise, similar kind of thing before. N was the number of steps that we took in a particular time. So number of steps that we took per particular time. So if we multiply it by the time taken to move by each step, so the time taken to move that tiny little distance now. So tau is time taken to move that tiny little distance for each step. So therefore, that is now going to become, we're going to call that t, capital T, we're just going to call that t, okay? Now, basically, the idea is that we want to basically take this one big step, right? And we want to now make it smaller and smaller and smaller. So in other words, we want to make it smaller and smaller and smaller. So we're making it lots of tiny little steps. So what we're basically doing there is we're making delta. So we're making the distance that we move in each step. We're gonna make our delta go to 0. We're gonna make that smaller and smaller and smaller. That little distance there, we want to make it go smaller and smaller and smaller. We want to kind of push it inwards and push it inwards. Okay, and the same thing for tau. We want to take, we want to try and condense the time taken for each step. We want to try and condense it to 0. We want to make it smaller and smaller and smaller and smaller. We want to take it less and less and less time. Okay, and what we're going to have as a result, well, we're going to make, the position that we end up at. I'll come on to that in a minute. But the number of steps that we take, if we're taking smaller and smaller steps, and we're taking less and less time to complete each steps, then effectively we're just gliding. We're just gliding along it. So the number of steps that we're taking is going to be infinite. We want to take as many steps as possible in just a tiny, tiny distance. Each of those steps is just going to be a tiny, tiny distance, and it's going to take hardly any time at all. So we want to effectively have the effect of just having a smooth gliding motion, effectively. Instead of sort of definite clunky steps, clunk, clunk, clunk. We want to just effectively move in a nice, smooth, straight line, like a snail. It's gliding along the ground, if you like. So we want to take the number of steps that we're taking is going to go to infinity. And as a result, m is also going to go infinity. M is our position. Okay, so therefore, as a result, we can go to any position we like. Because whereas before, we could only go to, in this example, from 0 to 1. So we can either end up at 0 or we can end up at 1. Well, now we can end up here or here or here or here. So the idea is that we can end up at any point along this line. So we can end up the number of positions that we can end up at is going to go to infinity, okay? Because we can go to an infinite number of places. If you like, how many numbers are there between 0 and 1? Well, there's going to be an infinite number of numbers, yeah? I mean, you should be fairly familiar with that. So in other words, this is the whole idea behind what we're going to do. We're going to basically make, our time steps and basically going to make each step go to 0. We're going to make it so small, okay? And we're also going to sort of make more and more steps. Right, okay. Well, whereas before, Well, whereas before, what we had was that, if we had all the probabilities, the probability of us being in a particular time step or a particular position, given we'd taken a certain number of steps, was given by this thing here. Okay, so the probability of us being in a particular position, given that we've taken a number of steps, right? And we know that when we add all these probabilities together, that they must be equal to 1. Okay, so when we add all the probabilities together, okay, so probabilities together, so effectively we're going from minus n to n, so m goes from minus n to n. So if you like, this is the number of steps that we have. Got 0, and it's obviously going to be symmetric, so minus n to n. So the number of steps that we can have, so the positions that we can have, is going to be given by this, and it must always add up to 1 because that's the rule of probabilities. Yeah, all of the probabilities must add up to 1. It must add up to certainty. In other words, if it doesn't add up to certainty, which is represented by 1, then we've missed probabilities. Okay, because all of the probability, something must happen effectively, and so the probability of something happening. So therefore, we just take everything together, put everything together, and it must add up to 1. Okay, but look what happens if n goes to infinity. As n goes to infinity. Okay, the probability, so the number of steps that we take is going to infinity. We're taking more and more steps. Then the probability of ending up at a particular position effectively gets smaller and smaller and smaller. Yeah, because whereas before, you could end up at either 0 or 1 stage. Say if this is so maybe if I consider the left-hand case as well. So we have 0, we can end up at -1, or we can end up at 1. So just a one-step model, okay? So we start at 0, and we can either end up at -1, or we can end up at 1, right? Well, as we take more and more steps, effectively, the number of places that we can end up also increases. So therefore, the probability that we end up at a particular place must decrease. Whereas before we had the probability that we end up here or here is a half. So probabilities are half here, probabilities are half here. But now, as we take more and more steps, we saw in the example above that as we took more and more steps, we basically get smaller and smaller probabilities. We get a quarter for t equals 2, we get an eighth for t equals 3, and so on, and so on, and so on, and so on. So basically, the probabilities should decrease as we take more steps. Well, if we then take n to infinity, the number of steps that we're taking, if we take it to infinity, then therefore what we get is that the sum of 0 effectively. And that is obviously 0. So, we're just taking the sum of the probabilities, which is going to 0 as we take more steps, and therefore that becomes 0. It doesn't become 1. So therefore this doesn't work. So we have to kind of, rethink that. Another way, if you didn't really understand what that was, another way of saying it is basically what we're saying is that the steps are basically 0 because we're taking more and more steps. That basically the distance that we're traveling each time is getting smaller and smaller and smaller. So the step size is getting smaller. Okay, so it's almost as if it's not there. Well, the probability of not moving, so if nothing's there, then it's just effectively the same. This is such a small little distance, say from moving from there to there, such a small little distance that it's basically the same as not moving. Well, the probability of not moving is always 0. Probability of not moving is basically 0. So that's why, that's another reason why the probability should go to 0. Another reason for the probability going to 0, okay? Okay, so here's what we're going to do, and I'm going to try and present it sort of graphically, just hopefully so you can see a little bit better, right? So what I'm going to do, okay, I'm just going to consider my number line, okay, and let's say, for example, I'm at this position here, so I'm at x, right? I'm at x here. So I'm at this position here, right? Well, let's say that the distance which I move, is given by delta, right? So I can either move, I'm just going to scale this up, so I'm going to, enlarge it, if you like. See, in reality, it would just be such a small little sort of thing that you'd barely notice it. But I'm just going to scale it up. So the distance which I move, is going to be given by delta, so I can move either right or left by delta. Delta. So therefore, this position over here is going to be x minus delta, because I start at x, okay, and then after time 1, so after one time step, I either end up here at x minus delta, or over here, which is obviously x plus delta, because I move by a distance of delta each time. Okay? So that's what I've got there. Now, what I'm going to do, okay, so what I'm going to do then is I'm just going to write down the probabilities, actually. So the probability that I'm at this point, which is x, okay, after a certain number of time steps, which I'm just going to call n, is going to be given at that point there, okay? Probability I'm at this point here, so the probability that I'm at x minus delta, okay, because that's my position here, x minus delta, given that I've taken a certain number of time steps n, Okay, and the probability of here I'm going to write as probability that I'm at x plus delta. That's my position there, x plus delta, given that I moved to certain number positions n. Okay. Well, can you remember from probability that, if you want to take the probability of something, if you've got what's known as a PDF, which is effectively what I've got here, it's a probability density function, so in other words, I can draw it on a graph, then the area will give the probability. The area will give the probability. So what I'm just going to do now is I'm just going to get rid of those deltas there, okay, and I'm just going to consider one single step, okay, and I'm just going to put it symmetrically around the position that I'm currently at, so my position x. So this is, if you like, delta. This whole position, this whole movement in here is delta. Okay, I'm just going to drop that down there and that down there. Okay, well this position now is x minus, what's it going to be? It's going to be x minus delta over 2, because I've only moved, if I move to the left, okay, if this whole movement is delta, then this movement here is delta over 2, and this movement here is delta over 2 as well. Okay, so basically I'm either moving to the left by delta over 2, which is x minus delta over 2, or I'm moving this way to the right by x plus delta over 2. So all I'm just doing is I'm just considering a time step which are positioned symmetrically around the mean. And effectively I want to now try and find the area of that thing. Okay, the area of that thing. Well, I'm going to basically say, well, okay, the height of this rectangle, or the height of this rectangle, I'm just going to call u. Okay, so that's the height of my rectangle. Now, what is the height of that rectangle? Well, I know that the area will correspond to the probability. I know that the area of this shape underneath here will correspond to the probability. So the area underneath this kind of rectangle, that will correspond to the probability. And what is it currently? Well, I've just said it's going to be base times height, right? So base at the moment, that distance there is delta. So it's going to be delta. Okay, and that height, which I've just called u. That height I've just called u kind of arbitrarily. I've just called it u. I want to call it something. That's u for height. So the height is going to be u. Okay. And so now I know how I can now find an expression for u. So u is just going to be probability over delta. Probability over delta. Okay. Okay, well this probability in here, I should sort of write this out properly. This probability in here is actually probability of mn. Okay, it's just the same as we had before. This is probability of mn. Okay, well what is m? Well, we know that x equals m times delta. Okay, and what do we have as well? We had t equals n times tau. So therefore m was equal to x over delta. X over delta. Okay, and n was just t over tau. N was just t over tau. So therefore I can just replace m with x over delta, and n with t over tau, just like that. So therefore I've now got a proper expression for u. Now this is quite interesting, because basically the whole idea is that as we go, it's using something called Stirling's formula, which you can look into if you want. There's a lot of awkward algebra involved. I'm just going to tell you the result. But yeah, you can look into it if you want to. But essentially what it's saying is that as we go from a discrete case to a continuous case, like we're doing now, yeah, we're going from discrete time steps, where are we? We're going from a single discrete time step to suddenly being sort of gliding along. So rather than taking a single step like we as humans would do, let's try and draw this. So rather than taking a single step as we as humans would do, okay, what we're going to do is we're going to think like a snail now. And we're effectively just going to glide along the ground. So rather than taking, going from here to here, we're now going to just glide along the ground. Okay, and that's effectively what we're doing here. So we're going from discrete continuous. Well, discrete case, we saw that discrete case had a distribution or a characteristic associated with it, and that was, of course, the binomial. Okay, binomial. Yeah, and we kind of looked into that, the kind of whole properties of the binomial, or characteristic properties, or the characteristics of the binomial in this case. Okay, well, basically, as we go to the continuous case, what Stirling's formula basically tells us is that as we go to the continuous case, so in other words, as we take more and more steps, I mean, you've probably seen this in statistics, that basically as you take more and more data of something, it basically tends towards a particular distribution, and it tends towards the normal case. And basically Stirling's formula will give us the correct case in this case. So this is effectively just exactly what we're doing here, because we're taking delta to go to 0. So in other words, we're considering a smaller and smaller distance for delta. So in other words, these two things are becoming closer and closer to this sort of, the x minus delta and the x plus delta are coming closer and closer to my x, until effectively they're almost on top of it. So in other words, the distance between them is so small that if we move them any closer, they would be exactly the same. Okay, and that's basically the idea here. So as we take more and more time steps, this is effectively what's happening. And the whole idea is that we're going from a binomial distribution into a normal distribution. Okay, well, if you remember, there is a formula for a normal distribution, and actually Stirling's formula will give it to us. We had u equals, just from above, we had u equals p of, it was x over delta, okay, and this was that was t over tau, wasn't it? T over tau, over delta, okay? Then basically what it tells us is that we approach something that looks like a normal distribution. Well, if you remember from normal distributions, that, we had this very kind of awkward formula. Let me just try and think of it. It was, if I just remember, it was p of mn. I think this is right. Something looks like this. The probability will be given by something like square root of 1 over 2 lots of pi times, well, it'll be n in this case, square root of that, times e to the minus m squared over 2n. I think it's something like that anyway. Something like that. Okay, so it's just basically a PDF of a normal distribution. Okay, well, basically now we just sub in sort of our m's and our m's and n's, and basically this is what it comes out as. So if I just write it down, it basically looks something like this. You don't have to kind of worry too much about where this comes from. It's a lot of awkward algebra, but effectively hopefully you can see the relationship between that and that. So we end up with 2 pi t delta squared, okay, times by e to the power of, here we go, minus x squared times tau over 2t lots of delta squared. Okay, so that's effectively what we end up with. Don't worry about where it comes from. It's a lot of kind of algebra basically going on, but it's basically using something called Stirling's formula, and hopefully you can see the comparison between that and that. So this is basically what we end up with. Okay, so u is kind of following a normal distribution. Okay, so let's just remember about what we want to try and do. We want to try and make m go to infinity, so our position effectively goes to infinity. The number of positions that we can end up with, we'll end up with an infinite number of positions. Yeah, if you like, you're going from 0 to 1, you can end up at an infinite number of positions in between 0 and 1. Okay, we're also trying to make n go to infinity. So the number of time steps that we're taking, the number of steps that we're taking more and more steps, okay? And so as a result, we're making delta go to 0. So the distance between each step, we're trying to make smaller and smaller, okay? And the time taken to travel each step, we're trying to make 0 and 0. We're going to make 0. So effectively, we're trying to make a nice, smooth, continuous motion. Okay. Well, basically, if we take the limit of the ratio of delta squared over tau, okay, so hopefully you can see delta squared and tau in there, delta squared and tau in there, okay, or rather not in there, in here. So we take the limit of that. So basically we're making delta go to 0 and tau go to 0. Okay, because that's what we're after. We're basically making those things go to 0. Then basically this approach is approaches a special value. We're going to talk about this a little bit later on, but it's the diffusion coefficient, okay, and we call it D, and it actually approaches 2 times D, so 2 times our diffusion coefficient. We're going to talk about that later on in the video. Don't worry about it too much now. All you have to basically know is that, the limit of that thing, as we try and make, the time steps smaller and smaller, it goes towards this thing called a diffusion coefficient. And that is non-zero. So basically, if we make time steps smaller, so effectively what we're doing is we're making it go to a continuous distribution, and it approaches something called the diffusion coefficient. Okay. And notice as well that we've also got tau and delta squared there. So basically, if we take the ratio of delta squared to tau, so we've got that in there and that in there, then it approaches something called the diffusion coefficient. It's 2D. Okay, so now what we can do is we can just replace that thing in there. So these two things in there is going to go to, what's it going to go to? It's going to go to 4D, so make this 1, and that's going to go to 4D. Why? Because, well, it will go to 2D, but of course it's the square root. So we want kind of the thing before we take the square root. So if the square root of tau over delta squared should should go to, we want it to go, or actually no, what am I doing? Of course not. Okay, let's get rid of that. Sorry if I confused you there. That is just going to be 2d. Okay, we're just going to replace delta squared by tau by 2d, but of course it's going to be 1 over 2d, because we want to replace tau by delta squared, which is what we've got inside the brackets. What do we have here? Let me, if I just write that out again. So we had, what was it? Tau on the top and delta squared on the bottom. Okay, and I want to replace that. Well, tau over delta squared, if delta squared over tau, when we take the limit, goes to 2d, then tau over delta squared should go to 1 over 2d. Should go to 1 over 2d. So in other words, we can just replace that with 1 over 2d. Okay, but we've already got a 2 here and a 2 here, so it's being multiplied together. So now let's just replace it by 4. So sorry, I was being confused by what I had down in my notes. Okay, I'm just going to neaten this up a little bit. So 4 pi dt, where d is just a diffusion coefficient. Okay, diffusion coefficient. Okay, and a similar kind of thing here. So let's just replace this by 1 over 2d. Just replace this by 1 over 2d. Okay, and of course we've got 2 times 2 here. Got 2 times 2 here. Oops, 2 times 2, which is going to come 4. We've still got a t in there, so therefore that's what that thing's going to come. And this is as we take the limit. So we take the limit as delta and tau go to 0. So basically, we make tau delta go to 0. This no longer is an approximation. It's now an equals. Okay, and it goes towards this thing called the diffusion coefficient. Okay, and that makes it a little bit more kind of, we will look at that. We will effectively look at that in a little bit later. Okay, it's a very important thing. It's a very important thing, and it basically what it does, it measures the speed of dispersal of our walker. So in other words, how quickly it spreads out in space. So in other words, if we start at 0, okay, how quickly does it get to here, or how quickly does it get to here? So basically, how quickly does it spread out? Because obviously, we've seen, where are we? Right at the beginning of this video, let's try and find it. We've seen right at the beginning of the video that if we start here, you can see that it just kind of spreads out, right? It spreads out like that, or it spreads out like that. So it kind of spreads out in a way. And, that is known as the diffusion coefficient. How quickly it happens is known as the diffusion coefficient. But don't worry, we're going to come on to it. We're going to come on to it later. Which, as expected, this thing in here is just a normal coefficient. Okay, it's just a normal distribution with mu equals 0, and our sigma squared, or our variance, should just be 2 dt. And of course, you can verify that if you kind of get up the PDF for a normal distribution. Okay, it looks a bit like a normal distribution to me, so I'm satisfied to say that. Okay, but effectively this looks like a PDF for a normal distribution with these kind of parameters, so 2 dt. So that's effectively what we end up with. And actually, we can draw, what actually happens. We can draw what actually happens. So let's suppose that we keep the same time. Well, if we have a higher diffusion coefficient, then effectively we kind of, it spreads out over a larger time. Okay, so this is a higher diffusion coefficient, so D2. It's a higher diffusion coefficient, or D1. Okay, and if we have a higher, if we keep so this is same time, it's the same t. If we have the same diffusion coefficient, and let's suppose that T1 happens higher than T2. So if T1 happens like this, and if T2 is much larger, okay, then therefore we're going to end up with something like this as well. So that's just kind of showing how time and diffusion coefficients affect it. Now, the thing is with this approach, it cannot deal with a more complicated scenario. So, for example, if an animal is more likely to move or be attracted to move left than right. So, for example, why would an animal be more likely to, move left or right? Well, say, for example, if it's attracted towards food. Okay, so this scenario can't deal with this. So say, for example, if there's food on the left, say, for example, if we start here, okay, there's food on the left and there's no food on the right. Okay, so although this is kind of a really simple introduction, it's basically it can't deal with that because obviously in this example, the animal is more likely to be attracted towards food. It wants food, right? So it's more likely to move left than right. But this example, this sort of kind of model can't really deal with that. So a lot more complicated. But it's a good kind of introduction. Okay.